Hi, Jim Heffron. These are my lessons in Calculus 1. So today we're going to do the homeworks for the definition of the rate of change of a function. I talked before in the previous slide about how this is a very important definition. I kind of imagine that if aliens, come to Earth and they're trying to decide whether we're worth bothering with, that they might have a checklist, and on the checklist they'll the first one invented fire, yes, and the second one invented the definition of rate of change of a function. I mean, it's that important. It's a big one. It is central to our understanding of how things work. Okay, so a lot of homework to do. One of the things that you'll see in the homework is that I've got an even numbered homework question, and that's just because I'm trying to pick ones that I think are most helpful for future work. So a lot of stuff to do. Off we go. Let's see. Then I've got to bring up the doc cam, and the first one is section 2.3, number 13. So I've got it here. Section 2.3, number 13. Again, this is the Stewart Calculus book, just to give credit for the folks whose work I'm showing. Here we go. The limit as t goes to 4 of t squared minus 2t minus 8 over t minus 4, and it says evaluate the limit. Okay, so the limit as t goes to 4. Limit as t goes to 4 of t squared minus 2t minus 8 over t minus 4. And so, we've all spent many hours working on factoring polynomials, and the reason for that is exactly this moment. It's that you need to do it at exactly this moment, and that's why you practiced it all those times. So this is going to be t minus 4, t plus 2. And now the bottom is t minus 4. We made the point many times that that at t equals 4, the limit is not in effect. We're talking about t's near to 4. So near to 4, you can cancel the t minus 4's, and you get the limit as t goes to 4, t plus 2. That's not a fraction with a 0 denominator, so you can plug in 4. Okay, so again, I'm reviewing a question from a previous section, because if you do that systematically over the course of the semester, every time you do one of these problem sets, you throw in a review from some previous section, and especially try to focus on the ones that might have given you trouble in the past. Well, then, you'll come to the exam and you'll say, oh, yeah, I remember that. And that is a good feeling. Okay, so next up, let's see, I'm looking at section 2.7, the new material for the day, section 2.7, and I'm thinking first about its example 2 I wrote down. Just picked some, trying to model what a person might do here who is trying to work their way through the material. So example 2, here we go. Says find an equation of the tangent line to 3 over x at the point 3, 1. And of course, there's an answer there. I could peek at the answer and say to myself, oh yeah, I know how to do that. But much better is to try it and find out you don't know how to do that, and then figure out what's the right answer. So we have f of x is 3 over x. And we're interested at the point of tangency is 3, 1. Okay, so there are 2 steps to the job. We have to find the rate of change, and then we have to plug it into the point-slope form of the equation of the line. So we know how to find the rate of change. We take the limit as, let's see, the limit as h, sorry, I lost track here. H goes to 0 of f of x plus h minus f of x over h. In this case, x is 3, so we're taking the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. And there are 2 3's in this problem, so just to make sure I've said it, not this 3, this 3. Okay, so the anchor point, the point of interest, is x equals 3. Okay, here I go. So that's the limit as h goes to 0 of 3 over 3 plus h, and 3 over 3 all over h. I know 3 over 3 is 1, but I'm just trying to do it one step at a time. Oh, UPS guy here, why the dog's barking? Anyway, so let's see here. I've got a combination of fractions in the numerator, so probably the simplest thing I can do is to try to figure out if I can break that down to a single expression in the numerator. And so I guess I'm looking at the limit as h goes to 0. I'm ignoring the bottom for just a moment. And let's see, I have 3 over 3 plus h minus 1. So I think I've got 3 over 3 plus h, and I'll rewrite 1 as 3 plus h over 3 plus h. And then I got a common denominator, and I'm just hoping, got my fingers crossed, that solves my problem. The problem, of course, is that the limit of the denominator is 0. So the limit as h goes to 0 of, we'll copy the h to the bottom, and it's 3 minus 3 plus h all over 3 plus h over h. I see the 3 and the minus 3, so I've got the limit as h goes to 0 all over h, and a 3 minus 3, and so I think I've got a minus h on top and a 3 plus h on the bottom. And of course, my eyes light up because I see there's an h and there's an h. So I'm going to cancel those h's, and it's a little bit of writing here, a couple of lines, but I've got the limit as h goes to 0 of minus 1 over 3 plus h. That no longer has a denominator with a limit of 0. Now the denominator's limit is 3. So the smoke has cleared, and I've got minus 1/3. And I'll finish by plugging into the point-slope form of the equational line. So tangent line. So remember, it's y minus y1. You have to memorize it. Is slope times x minus x1. And so I'm looking at what y minus 1. I'm pulling it out of here. Y minus 1 is equal to minus 1/3 times x minus 3. Okay, and if you'd like to get the y equals mx plus b, feel free. Go nuts. Sometimes the answer in the back of the book is maybe it's y equals mx plus b, and so in order to check, you got the answer that the back of the book got. So, but anyway, so something like that. This is an example, I guess. So they may write it in some different form, and you have to check. But this is a perfectly good form of the equational line. Okay, great. So off we go now to the exercises. It says number 11 and number 15, and also number 20. I got to find the darn thing. Here's number 11. Okay, so it says cliff diver plunges from a height of 100 feet above the water surface. Distance that the diver falls in t seconds is d of t is 16 t squared. After how many seconds will the diver hit the water, and with what velocities does the diver hit the water? So I've got to figure out 16 t squared it's equal to 100 for what t? And then when I find that, then I'll find the rate of change of the position function, the rate of change of 16 t squared at that number. All right, so let's say, here we go. So 16 t squared equals 100 is part A. So in how many seconds does the diver fall the 100 feet? So let's see, I guess I get t squared equals 100 over 16. So t is equal to, what happens when you take the square root of both sides? Don't you get 10 over 4? I suppose we could write that as 5 over 2. Okay, so I now know that I'm interested in the rate of change of this function at 5 over 2. All right, so the limit as h goes to 0 of, they don't call it f, they call it d, but d of 5 over 2 plus h minus d of 5 over 2 all over h. D of 5 halves plus h minus d of 5 halves all over h. And I'm pretty confident that we'll get to some kind of algebraic expression. We'll figure out a way to make it so that the denominator does not have a limit of 0, and then we'll be home free. Okay, so let's see. Then I'm looking at limit as h goes to 0 of, well, let's see, 5 halves plus h, I got to take 16 times 5 halves plus h squared. So that's 5 halves squared is 25 over 4. 25 over 4. 2 times 5 halves times h is 5h, and h squared. And then minus d of 5 halves is 16 times 5 halves squared. Okay, anybody can make a mistake. I think I got that right, but anybody could make a mistake. So if I did, I apologize. I'm going to cancel canceling is a frequent experience here. So I'm going to cancel the numbers, and I end up looking at the limit as h goes to 0 of 16 times 5. Let's see. So that's 80h plus 16h squared all over h. And again, the difficulty here is that the limit of the denominator is 0. We got to figure out, but we've seen this many times here at this point. So limit as h goes to 0 of factoring h out. Remember to factor it out of every term over h. And we're looking at 80 plus 16h. So I cancel the h's, and I'm looking at the limit as h goes to 0 of 80 plus 16h, and of course I can simply plug in because this is a polynomial in h, and so I'm looking at 80. So the velocity when the diver hits the water is going to be 80. Okay, great. What's up next? I've forgotten already. So 15. So 15 says a particle starts by moving right along a horizontal line. The graph of its position is shown on the figure. When is the particle moving to the right? When is it moving to the left? When is it standing still? I better change from my pen to my pointer. And then it says, draw a graph of the velocity function. So it seems to me here, this is the graph of its position function shown in the figure. So the position is increasing. So so it seems to me that it's moving to the right, then it's stationary, it's paused, then it moves to the left, then it's stationary, again it's paused, and then it moves back to the right again. So again, just to have done it in case a person looked down. So moving to the right, stationary, moving to the left, stationary, moving to the right again. All right, and then it says draw a graph of the velocity function. So this is a concept problem where they're asking me to think about what is the what is the meaning of the rate of change. So it seems to me the slope of this line is 3 up and 1 over. So velocity is 3, then velocity is 0, then velocity is minus 2, then velocity is 0, then velocity is 1. So velocity is 3, then 0, then minus 2, then 0, then 1. Let's see if I draw that out as a graph, but at this point, do I really need to? So let's see. I need to go horizontally 0 through 6. So 2, 4, 6, and I'll put in the intermediate numbers. And I need to have a minus 2, so I've got 3, 0, and minus 2. So let's see, I got a red pen, I hope it works. Velocity is 3 for the first second. Velocity is 3 for the first second, so this is v of t. Velocity is 3 for the first second, then it's 0 for the next second. Then velocity is minus 2 for the next second, minus 2 for the next second. Then it is 0 for the next second. And then velocity is 1 for the next 2 seconds. Okay, so it's a concept problem, one of these problems where they're asking you to think about what is the meaning of rate of change. Don't want to lose track that it's all about something. It's not just manipulating, h's and moving things to the bottom of the fraction. It's about something. It's about, in this case, the rate of change of position. And then the last one, I decided to ask an even one, number 20, because frankly, I thought it was a useful problem. So I'm going to change paper for that because it's a bigger problem, but I think it'll be useful. see here. So number 20 says find, I don't need the book. It says find f prime of a. So find, there we go, find f prime of a, where f is 5x to the fourth, and a is minus 1. Okay. Okay, so we're going to have to take minus 1 plus h to the fourth power. So we're going to need minus 1 plus h raised to the fourth power. So I like this problem because it gives me an opportunity to remind a person how to expand a binomial in this case. So just a reminder here. So a reminder is that a plus h raised to the fourth power is a to the fourth plus 4a cubed h plus 6a squared h squared plus 4a h cubed plus h to the fourth. And the point of the reminding here is that I'm reminding a person how this works. See how the terms go. It's a to the fourth, a to the third, a to the second, a to the 1, and there's no a at all there. And then there's no h, 1h, 2 h's, 3 h's, and 4 h's. And what about the coefficients there? The coefficients are 1, 4, 6, 4, 1, and they come right out of Pascal's triangle. This is the fourth line of Pascal's triangle. And of course, you can reproduce that over on the side of the paper, or you can have it memorized like I do, down to some line, or you could reconstruct it if you had to. Okay, so I think I'm looking here at minus 1 plus h raised to the fourth is minus 1 to the fourth plus 4 times minus 1 cubed plus h, so that's plus 4 times minus 1 times h, 6 times minus 1 squared times h squared, 6 times 1 times h squared, 4 times minus 1 times h cubed, 4 times minus 1 times h cubed, and h to the fourth. Maybe parentheses there. So kind of a complicated expression, and it gave me an opportunity, this problem gives me an opportunity to remind a person of this, which we're going to need not too long, this kind of thing. All right, great. I'm going to cancel the minuses, see how it goes. So I get here a 1 minus 4h plus 6h squared minus 4h cubed and plus h to the fourth. All right. So I'm ready now for the difference quotient, the limit as h goes to 0 of it's 5 times minus 1 plus h to the fourth minus 5 times minus 1 to the fourth all over h. Okay, limit as h goes to 0 and it's 5 times this expression up here, so I'm going to copy the expression down. 1 minus 4h plus 6h squared minus 4h cubed plus h to the fourth. Take away 5 times 1. And the pattern we've seen so many times here is that there's a plus 5 times 1 and a minus 5 times 1. So it cancels. And in particular, what's left, everybody in what's left, all of the terms in what's left, has an h. So we've done this a number of times now. We're starting to get to be able to say, aha, this is one of those. So this is one of those. Limit as h goes to 0 of, cancel the 5 times 1, and you're looking at over h. You're looking at 5 times minus 4h plus 6h squared minus 4h cubed plus h to the fourth. You could bring the 5 in, leave the 5 out, doesn't make any difference. Okay, I know I'm going to factor out an h. So the limit as h goes to 0 of h times And we can see the end of the problem now. We're going to cancel those h's, and then we'll plug in h equals 0, and then we'll be home free. So what's left when you factor out an h? Of course, you're factoring out of each one of these terms. So I've got 5 times minus 4 plus 6h minus 4h squared and plus, I ran out of room, h to the third. Sorry about that, I ran out of room. Cancel the h's, and what's left is limit as h goes to 0 of 5 times minus 4, so that's minus 20. And then just multiply through here. 5 times 6 is 30. 5 times 4 is minus 20. And a 5. Of course, all of these terms that have h's in them, when we go to a plug in h equals 0, just disappear, and we end up with a minus 20. And again, I keep saying this over and over again, but I can't say it too often, that what's different between what's here and what's here is that I can't plug in h here because the limit when h goes to 0 of the denominator is 0. So I can't plug in h. But once you cancel the h's, I can go ahead and plug in h because I'm now looking at a polynomial. And in the special case of a polynomial, you can just plug in the value of h equals 0, and you get minus 20. Okay? Okay, and so taking it back to the beginning here, I'm reminding a person what happens when you expand a binomial to some power, and the answer is you get these expansions here. It so happens that the one that matters, remember that the a to the fourth, remember the 1 here and the 1 here will end up canceling. So the one that matters is this one here. 4 times a cubed times h. What do I mean by matters? What I mean is that it ends up being there's the 4, there's the 4, there's the 4, and there it is down there. All of the other terms, the thing with an h squared, the term with an h cubed, the term with an h to the fourth, they will all end up, when you get to the bottom, they will all end up not mattering when you take the limit as h goes to 0. So the critical thing is this one right here, and we'll see later when we get a chance to look at it, we'll see that what is most important here is this term right here. Okay, the term that's linear in h. Okay, very good, very good. Looking forward to the next set. We're starting to make some real progress now. Great.